So, good evening, everyone. Welcome to the second session on live tutorial sessions on the course Fundamentals of Electronic Device Fabrication. I am Sandra Krishnan, and last week we had gone through the basics of whatever was happening in our course in the first week, and we had solved few problems. So, this week we'll be doing the same. So, does anybody of you have any other doubts regarding the registration or the examination and so and so? First, we can just see through that, and then we'll start with today's summary session followed by a few question answers related to this week. So is there anything else, general queries that I can help you with in the meantime? You can ask now. Am I audible to you all?
Yes, ma'am.
Yeah. Okay, thank you. So I think nobody has any questions. I'll just switch off my video for better clarity of voice, and then we can start with today's session. So if you have gone through the summary PDF that has been uploaded as part of the assignment, we can see that in this week you were introduced to the concepts of layering, lithography or patterning, as well as probing. Those were the three lectures that was going on. So the first lecture was in depth on the oxidation or the layering operation. So can anybody tell me from previous week what type of a layer growth was, what type of a layering operation was oxidation? Can anybody tell me from the discussions on previous week, like we had discussed that there are two types in which we can, sets of processes that we can use for the layering operation. So two types of layers were there. So oxidation comes under which process? Can anybody tell me? Like two sets of operations were there. Yeah, yeah. Tell me please.
Is it physical?
No, like not that differentiation. Like oxidation was there, PVD, CVD was there. So oxidation comes in what types of layering? Is it a grown layer or
It's a deposition.
sorry?
Deposition?
It's a grown layer actually.
Okay.
Yeah, oxidation and nitridation comes in film growth, right?
Right.
Yeah, deposited layer comes through CVD, thermal evaporation, sputtering, electroplating, etc. So oxidation is a type of grown layering operation. That is using the substrate itself, as we can see here, using the substrate itself by consuming a part of the substrate, a new layer will be formed. So in case of oxidation, there is dry oxidation and wet oxidation. So if you see a dry oxidation, it will be reacting with what? It will be reacting with oxygen. And in wet oxidation, it will be reacting with steam. So, and based on this, we had seen an equation to find out the thickness of the grown layer. So this was the final equation that we derived, that is d prime is equal to 1.88 d, where d prime is the total thickness that has been grown and d is the consumed thickness. So is that clear for all of you? Yeah, so if you remember the equation, this particular equation, if you have gone through the lecture, it was equated using the number of moles. So number of moles means given mass by molar mass, right? So given mass, here they have separated as density into volume, where D is the thickness and A is the area. So when we multiply both of that, we get volume. Volume into density, we will get mass. So given mass by molar mass of silicon will be equated to the given mass by molar mass of SiO2. So that is how we finally got the thickness of the grown layer in the oxidation process. So here it is used using silicon itself. That is why we are able to cancel In other cases, so there is a question in your assignment, I think, where different materials are deposited and you are asked to find out the thickness of the grown layer. So in that case, instead of cancelling, you will have to substitute the value for each of these. So I hope that's clear in case of wet oxidation and dry oxidation. Then we saw what were thin and thick oxides. So in case of thin oxides, it had a linear oxide growth and thickness was proportional to time. But in thick oxide, it has a parabolic growth process and thickness was proportional to time power 0.5. And in thin oxides, growth rate will be constant, and in thick oxide, growth rate will decrease with time. So thin oxide is a reaction control process and thick oxide is a diffusion control process. So can anybody recollect from the lecture and tell me what would be the average thickness of a thin oxide and thick oxide? Like less than how much, greater than how much? What would be a thin oxide and what would be a thick oxide? Does anybody recollect what was thin oxide and what was thick oxide? Okay, just a random guess you can give. If you're familiar with the topic of electronic materials, then you can give me a random guess.
Around 100 nanometers.
Yeah, for thick oxide, there will be a few hundred nanometers. So a thin oxide will be much less than that, right? In the range of 30s or 50s. So that will be a thin oxide, and the thick oxide will be in a range of 100 to maybe about 500 nanometers or so. Is it right? Yeah. So that's correct. And now coming to reaction controlled versus diffusion controlled process. So can you tell me what would be a reaction controlled or diffusion controlled process? Diffusion controlled, I think you can answer from the name itself. Like what would be the limiting feature? So this reaction control or diffusion control means that the factor which limits this particular reaction or particular growth in case of thin oxide is the reaction. The reaction would be depleted. So when the reaction is depleted, the final thickness would be reached. And in case of thick oxide, so the final thickness will be reached when diffusion is getting limited. So what is the difference between reaction controlled and diffusion controlled? What is reaction controlled process and what is diffusion controlled process? So for answering that, basically we know the three processes will be happening during this SiO2 formation, right? So first one is the oxidizing species has to be transported from the bulk of the substrate to the oxygen gas interface, oxide gas interface. That is one process. Then diffusion has to happen through the oxide layer. Finally, reaction has to happen between silicon and oxygen to produce the new oxide layer. So when we are talking about reaction controlled, it means that the Si-SiO2 reaction will be limited. So when the Si-SiO2 reaction is completed, it will reach the final thickness. And also we should note that thin oxide process takes place at lower temperatures. So next in case of thick oxide, we are telling that it is a diffusion control process. Diffusion control process means what? Supply of the oxidizing species to the interface of Si and SiO2 will be limited. So that the diffusion process will stop, and when the diffusion process stops, the silicon oxide formation will be stopped. So is that clear?
Yes.
Yeah. So thing you have to keep in mind is that three processes will take place whether it is thin or thick oxide. First is oxidizing species has to be transmuted. That is, it has to come from the bulk to the topmost oxide gas interface. Then diffusion has to happen through the oxide layer, and also reaction has to happen between Si and SiO2 to form the new SiO2 layer. So in diffusion, in thick oxides, diffusion will be the controlling process, and in thin oxides, reaction will be the limiting step. So that is the case. Now, the second lecture was on doping, if you remember. So in initial class itself, we had given a light introduction to what are the different types of doping. So one is thermal diffusion and one is ion implantation. So thermal diffusion is a very high temperature process and we can use either solid, liquid or gas for converting them into dopant atoms. And here if you see that the maximum concentration at the surface and it goes on reducing as we go into the substrate. And also if you observe there is a large amount of lateral spread happening here. So in ion implantation, the thing is it's a low temperature process. It is a much more controlled process. Here the dopants are converted into the form of ions. So in thermal diffusions, those were atoms itself. Here they are converted into ions and maximum concentration is at some depth below the surface. So can anybody remember what this depth was called? Like that where maximum concentration is. There was one particular word for that. Does anybody remember?
Is it a range?
Yeah, it's range. So the maximum concentration will be at some depth below the surface and that depth is known as the range of the ion implantation process. So and there were few equations or of how we can find out the concentration of dopants present in the case of thermal diffusion and ion implantation. So the basic equation that governs thermal diffusion is D is equal to D0 e raised to minus EA by KB into T. So we said that in thermal diffusion, liquid, gaseous and solid sources are possible. So whenever we are using a liquid or gaseous source, it will be an error function solution. So error function, in case you are asked to solve during the exam, you will be given a chart where you will find the values of ERF. So this x by 2 root dt, this will give a particular value and its corresponding error function value will be given to you in that chart. So using that correlation, you will have to find the concentration at. So Cxt basically means that the concentration at this depth of x at a time of t. So also in case of liquid and gaseous sources, the surface concentration will be constant, which is given by Cs. So now when coming into solid sources, so the concentration at the topmost or the depth or the T will be given by Qt by root of I dt. And I'm substituting that and using an exponential relation, we will get the concentration at a depth of x and at a time t. So it will be following a Gaussian solution. So you might be asked in thermal diffusion, which of the following follows of the Gaussian solution? So whenever it is Gaussian solution, we should correlate that it's a solid source. And whenever it's an error function solution, it will be a liquid or gaseous source. So ion implantation process, so this is a high temperature process. This thermal diffusion process, it is a high temperature process. When we are coming to ion implantation, as I mentioned earlier, it's a controlled process, but it is a low temperature doping process and high energy ions will be impinged onto the vapor and the maximum concentration below the surface will be known as range. And one more factor in case of ion implantation is that it requires post-implantation annealing or heat treatment. So if you ask why we need such heat treatment means that whenever this ion implantation process is happening, the high energy ions will impact the substrate, right? So this high energy impact can produce some certain amount of defects or displacement of the lattice of the substrate. So in order to remove those defects or to strengthen the lattice or reduce the lattice distortion, we will have to do post-implantation annealing or heat treatment. So that is the case with ion implantation. So is that clear? So I think that was all about ion implantation and thermal diffusion. Yeah. So now I can ask a general question. So why do we need doping? So what is the reason for doping? It's a generalized question. So you can give your thoughts on why doping is required in case of semiconductors.
To form junctions, change electrical properties.
Yeah. Then you're also forming junctions. That is one correct answer.
To control electronic properties.
Yeah. So that is the main thing, to create junctions or to control the electronic properties, the conductivity or the potential required across the junction, etc. We need to do the doping process. So the doping process will be done using ion implantation as well as thermal diffusion. So things to note is that in case of thermal diffusion, solids will be following a Gaussian distribution kind of solution and liquid or gaseous sources will be following an error function solution. And in thermal diffusion, maximum concentration will be at the surface and there will be a large amount of lateral spread. In ion implantation, maximum concentration will be at a certain depth and that depth is known as the range. And in case of ion implantation, it requires post implantation annealing as well. So now when talking about thermal diffusion, it's actually a two-step process. First, we have to introduce the dopant ions, and then by giving the temperature, we have to drive in these atoms. So thermal diffusion is a two-step process. So first is introducing the dopant atoms, that is known as deposition, and finally drive it. That is the dopants has to be driven into the length of the substrate by giving them temperature. So that is another case, that is another thing that is related to thermal diffusion. Now, anything else related to dopant from last week? I think not. Yeah. So now the final thing that we had seen in the last week was lithography. Right. So what is meant by lithography? Anybody?
And the process of transferring the pattern onto the substrate wafer.
Yeah. So lithography is the process of transferring the pattern onto the semiconductor substrate. So it is the most important step in miniaturization, and newer patterning methods are being developed so that smaller and smaller circuits can be modified onto the substrate. So basically using lithography we can create a pattern with specified dimension, and also we correct or adjust the placement of the pattern with respect to the basal crystal orientation so that maximum efficiency can be achieved. So once lithography is done, it will be followed by again layering to add more layers or complexity to the circuit, then etching, etc. So the first step will be lithography. So in lithography, we will be using what is known as a mask or a reticle, which is a hard copy of the design. This design will then be transferred onto the substrate. So there are like so then comes what is known as photoresist, right? So there are two types of photoresist. One is positive and one is negative. So what is the difference between a positive and negative photoresist? So basically photoresist is a light sensitive material which is deposited on top of your sample or wafer. So in photoresist itself there are two types. One is a positive photoresist and one is a negative photoresist. So can anybody tell me what is the distinction between these two?
Positive photoresist allows the light to pass through it and it is soluble to the light.
Yeah.
And negative photoresist is insoluble to the light.
Yeah, so basically, positive means that exposure to light makes it soluble. Negative means that exposure makes it insoluble. So once it becomes soluble, when we are using an etchant or if it's an evaporating substance, means that when it is removed, it becomes more soluble in case of positive. In negative, it's the reverse, means that exposure makes it insoluble. So that is the case with positive and negative photoresist. So what all are there in a photoresist? Usually a light sensitive polymer, which means that its structure changes on exposure to light. Then it will be having a solvent and finally a sensitizer, which helps in initiating the reaction once it is exposed to the light. So these are the components that then they'll be having additives in the form of dye. So these are the four things that are usually present in a photoresist. So there are two types, positive and negative photoresist. So one more thing in case of positive photoresist, it directly transfers the design. In case of negative photoresist, what happens? It transfers the negative of the design, that is the inverse of the design onto the substrate. So that is the difference between positive and negative photoresist. Also, if we see this particular image, we can see the series of steps that are followed. So first the substrate will be cleaned, then we will apply the photoresist on top, then we will give a soft bake. Soft bake means that it will be heated at a light temperature so that the solvent will be evaporated. So it's usually performed at a temperature of about 90 to 100 degrees Celsius. And then after that, we will align the mask on top of this photoresist and we will provide the exposure. So once that is done, we will allow the resist to develop for a certain period of time. And after that, we will do the hard bake. So the hard bake is basically used for hardening the pattern that has already been transferred. So once that is completed, so the resist will be inspected whether it has been completely patterned or not. And finally, we will do a chemical etching so as to remove the oxide layer. And once that is done, the remaining of the photoresist will be stripped. That is the process I. The remaining of the photoresist will be stripped, and finally it will be given or extended to electrical inspection and so on. So these are the basic processes that are happening in lithography. So here we have again negative versus positive photoresist. So positive light exposure makes it more soluble, transfers the pattern directly. In case of negative, it is less soluble when exposed to light, and it transfers the negative of the pattern. And how do we usually apply the photoresist? It will be done using a spin coating process. So for spin coating, basically what happens is that the wafer will be held on to a rotating spindle using vacuum, and a drop of the photoresist will be dispensed onto the substrate using a pipette, or if it is automated using an automated dispenser, a sufficient quantity will be dropped onto the surface, and the spindle will be rotated at a predetermined RPM. So once it rotates, because of the centrifugal force, what happens is that the dispensed liquid will cover the wafer. So that is the spin coating process. So in using the spin coating process, the photoresist will be applied onto the wafer. So another type of lithography that is happening now is electron beam lithography. So can anybody tell me what is electron beam lithography?
Pattern directly drawn onto the surface.
Using
A beam of electrons.
sorry, can you repeat once more?
A beam of electrons.
Yeah. So instead of using a light exposure or using a hard mask for transferring the circuit, here pattern will be done using a focused beam of electrons, and it will be done on top of an electron sensitive film. So here the resist will be electron sensitive. That is the case of electron beam lithography. And in lithography, so here sigma is the feature size. So in order to control the feature size, we can tune either the wavelength of light that is used or the numerical aperture. So to improve, so smaller the feature size means more the resolution, right? So in order to reduce the sigma, we can either reduce the wavelength, UV and extreme UV lithography can be used, or we can increase the numerical aperture. So in air, usually Na will be equal to 1. If we are doing immersion lithography using oil or water, this Na will be having a higher value, and then sigma can be increased. Sigma is increased means that we can pattern smaller and smaller features onto the material. So another method is by using double patterning. So double patterning, what happens? In case of double patterning, it improves. So adjacent features will be added on to the substrate. So can anybody tell me what is double patterning? So here in normal lithography, we will be using only a single mask, but in double patterning, adjacent features will be designed simultaneously by using multiple masks. So that is the case with double patterning. Double patterning is also one other type of lithography that is used for improving the feature size. So these are two equations that are important while solving problems. Sigma is equal to k lambda by Na, where Na is the numerical aperture, and Na is equal to mu sine alpha, where mu is the refractive index. So usually when such kind of questions are asked, usually whatever is required for solving will be given to you. You need not like by heart the numerical aperture values of different liquids and so on. So I hope the summary was useful. For the past 1 week, 3 lectures were there. We had seen about layering operations, doping, as well as lithography. So have all of you done the practice assignment for last week? Have you completed the practice assignment?
No, I have not done.
Okay, so now we'll see the practice assignment. So okay, so first question is, which of the following fluxes is not associated with the oxidation process? So increase in oxide layer thickness, transport of oxidizing species from bulk to the surface, diffusion of the oxidizing species through the oxide layer, reaction of the oxidizing species to form a new oxide layer. So I had already mentioned whenever the oxidation process happens, three things will be happening. So out of these, one of the given options is not correct. So can you tell me which of it is? Three processes are there. So I mentioned during the recap that three processes will be taking place during every oxidation process. So if you remember,
Is it a reaction of the oxidizing species to form a new oxide layer?
basically in every oxidation process, oxidizing species has to be transported from the bulk to the oxide gas interface. So transport of oxidizing species from bulk to surface is correct. Then diffusion through the oxide layer, diffusion of the oxidation species through the oxide layer is the second thing that has to happen. Third thing is reaction with silicon to produce new oxide layer. That is reaction of the oxidizing species to form a new oxide layer. So what is not involved in the process is increase in oxide layer thickness during formation. So the answer to this question would be option A, increase in oxide layer thickness during formation. So option B, C and D are part of the oxidation processes whenever we are creating SiO2 oxide or any other oxide for instance. So is that clear?
I'm a
Yeah.
little confused. What does it exactly mean? Increase in oxide layer thickness during formation?
Basically, they are asking which of the following fluxes. Fluxes means what? Flux means some kind of transport phenomena or something that happens in a particular direction with respect to time, right? So they are asking which of the following fluxes is not associated with the oxidation process. So here increase in oxide layer thickness during formation is not the answer. Can you say ma'am why? Oxide layer thickness,
Yeah,
yeah.
yeah, it is not associated with the flux.
Yeah, it's not associated with flux. It is the final result, right? They are asking what is happening during the process. Like flux is associated with the oxidation process. During formation, we won't say increase in oxide layer thickness. Increase in oxide layer thickness happens as a result of the reaction that happens of the oxidizing species to form the new oxide layer. So that is the flux that is going on. Increase in the oxide layer thickness during formation, not during the formation. Finally, the oxide layer thickness will be a particular value, a constant value, but it is not associated with the flux. So is that clear?
Yes.
Yeah. So next is which of the following is not part of the photolithography process. So I have shown you a picture, right? A series of steps. So which among these was not mentioned in those series of steps?
Sputtering.
Yeah. So is everyone going with the same answer? Sputtering was not a part of the process. So spin coating is used for applying the photoresist. Baking is used in two times, like either it will be a hard bake or a soft bake. Soft bake for removing the solvent, hard bake for like hardening the pattern that is already deposited, and exposure means that after applying the photoresist, we'll expose it to light. The only process that is not involved in photolithography here is sputtering process. So is that clear?
Yes.
Yeah. So next is which of the following statement is true regarding concentration profile with respect to doping from a gaseous source? So this gaseous source, so in the summary we had mentioned if it was solid it used to follow a particular dependence. If it was gaseous or liquid it used to follow a particular dependence. So if it is a gaseous source, what kind of a dependence will it have with the depth? That is C x of t will be a function of dash.
It has an error function dependence on the depth.
Yes. So Next is the process in which unreacted resist is removed after exposure is called
Developing.
yeah. Okay. And finally, which of the statements is true regarding positive photoresist?
They transfer the pattern directly from
From
the
the mask
mask
onto
onto
the
the.
wafer. Yeah. So positive photoresist means that they become more soluble on exposure and they'll transfer the pattern directly. Negative means that it will transfer the inverse as well as it will become insoluble on exposure. So they will transfer the pattern directly from the mask onto the wafer. So is that clear for all of you? Okay. So now we have completed the practice assignment. So are all these questions clear for all of you? So are these questions clear? Whatever we discussed right now?
Yes.
Yeah. Okay, so now that we have completed the non-graded practice assignment for week 2, now we will see a few additional questions that I've prepared. So these are the things that is there in week 2: layering, oxide formation, dry oxide, wet oxides, thin oxides versus thick oxides, doping, thermal diffusion and ion implantation, and different types of sources, the governing equations and reactions for all of these. Then lithography process overview: what are negative and positive photoresist, what are the processes involved, and what is finally the factors affecting lithography. So the first question is, it's a very simple direct question that we already discussed. The depth below the surface at which dopant ion concentration is maximum in ion implantation is called
Range.
range. Yeah. So next is, which among the following are examples of a solid and liquid dopant source? So I request all of you to take some time to use Google or any other source, or if you have prepared your notes, etc., to find out the answer for the second question. So it will help you in like creating a list of solid versus liquid dopant source. So which among the following are examples of solid and liquid dopant source? So you can take a few minutes to search and then tell me the answer.
Solid SB2O3.
Sp2O3. Okay, others? Okay. Somebody. Solid C, liquid B. Solid C, liquid B. Yes. Okay, two people have answered. Others? think, okay. Okay, so here if you see this is a table, and this table here we have given ASH3. ASH3 is gaseous, it is known as arsine. Then BBr3, it is boron tribromide, it is a liquid source. Sb2O3 is antimony trioxide, it is a solid source. And POCl3 is phosphorus oxychloride, it is a liquid source. So also if you are, if it would be better if you can differentiate these sources into whether it is a p-type or n-type source, because instead of asking for differentiate between solid and liquid open source, they can also ask to differentiate between p-type and n-type sources. So basically, is that clear? So this is a table where you can find the different sources and their state as well as whether they are p-type or n-type. So ASH3 is gaseous, that is not asked here. Here they have asked just for solid and liquid open sources. So BBr3 is liquid, Sb2O3 is solid, and POCl3 is liquid. Yeah, and in the first question, the depth below the surface at which dopant concentration is maximum is called range. Drive-in means the diffusion of dopants into wafer, and penetration depth means depth up to which the dopant penetrates, and diffusion length, it is given by a root of 4 dt in the Gaussian solution for solid sources in thermal diffusion. Those are the explanation for the other options. So take a moment to please read through these points as well as the table. So are these two questions clear for all of you? Hello?
Yes.
Yeah. So next is in oxide growth, parabolic law is obeyed under what condition? Thin oxide layer, thick oxide layer, when a reaction is the rate limiting step and when no oxide layer is formed. So one of them follows a parabolic rate law. So which was it? The summary we had already seen.
Thick oxide layer.
So basically, these are the difference between thin oxide and thick oxide. Thin oxide lies in the range of 1 to 100 nanometers. The average will be in the range of about what 30 to 50 nanometers. Thick oxides will be much greater than 100 nanometers in the range of 0.01, that is a few hundreds of nanometers to up to 1 microns. So thin oxide, it will be a linear growth rate, and thick oxide will be parabolic oxide growth. Reaction control, so here a rate limiting step is reaction, that is also in case of thin oxide layer, so it's not thick, right? So this will be reaction controlled, and thick oxide growth will be diffusion controlled. In thin oxide the growth rate is constant, here the growth rate decreases with time, and here thickness is proportional to time and thickness is proportional to the square root of time. So those are the difference between thin oxide and thick oxide. So parabolic rate law will be obeyed in case of thick oxide layer, or we can say if there was an option which was not called when diffusion is the rate limiting step, that also would have been an answer. Then either of the two will be correct. So is that clear?
Yes.
Yeah. So next is a typical thickness value for a field oxide layer is dash nanometer. 5, 50, 100 and 500. So based on the different features that are there in different semiconductor material, so this also you will have to find out from external sources. Take a few minutes to Google and find out the different thickness values for a field oxide layer. So, if you have a doubt, what is field oxide layer? Basically, it will be thicker compared to a gate oxide layer. So, and in this particular field oxide layer, the field dielectric will not be there. So that is the field oxide. So it will be thicker compared to the gate oxide layer.
Five nanometer.
Like I told, it will be thicker, right? So basically, this will be the application versus thickness for different gates and oxide layer. So 6 to 10 nanometer or 5 nanometer will be usually observed in case of tunneling gates. 15 to 50 in case of gate oxides, dielectric capacitors, gates, etc. Then paired oxides will be in the range of 20 to 50 nanometers, 200 to 500 for hard marks and surface passivation layers. Finally, field oxides will be in the range of 300 to 1000 nanometers. So that is the typical thickness value for different oxide layers. So next is, which of the following statement is true regarding concentration profile with respect to doping from gaseous source? It is uniform along the depth. It has a Gaussian dependence on the depth. It has a parabolic dependence on the depth. It has an error function dependence on the depth. Doping from a gaseous source.
Error function.
Yeah. In the non-graded assignments, we had already answered, right? So, in case of concentration profile, that is for a gaseous source with respect to, we can say it has an error function dependence on the depth. So next is the diffusion coefficient is lower for a material A than B at the same temperature when the activation energy of A is greater than B, the activation energy of A is less than B. When the activation energies are equal, diffusion coefficient is independent of the activation energy. So in case of thermal diffusion, we had an equation. So first you have to identify that equation, and in that equation you have to tell me what is the role of diffusion coefficient and then the answer. So first, can anybody tell me which was the equation that will be used here in thermal diffusion? Please take a few minutes. If you have your notes, you might have probably noted it down after the thermal diffusion section.
Option
Yeah, can you tell me which is the equation?
equals to d naught into e power minus a by kt.
Yeah, and can you just give me an explanation for the others to understand? Like how you got answer A?
In the equation, it is e power minus ea, so it'll come in the denominator inversely proportional.
Yeah. So basically, this is the equation. D is equal to D0 exponential minus EA by KB into T. So the diffusion coefficient is lower for A than B. So diffusion coefficient, which of it is like in this equation, which is the diffusion coefficient? Please tell me.
D naught.
Yeah. So if D naught is the diffusion coefficient and diffusion coefficient of A is lower than B, then activation energy will be having an inverse relation, right? It's exponential minus EA by KB into T. That is why activation energy of A is greater than B. So is that clear? Is that clear?
Yes.
Yeah. So since the diffusion coefficient of A is lower than that for B, activation energy of A will be greater than that of B. So next is, in order to grow an oxide layer of 100 nanometer thick, the thickness of silicon consumed is approximately dash. Option A 25, option B 50, option C 100 and option D 200. So initially we had seen an equation for D is equal to something of B prime. Using that equation you will have to solve. Please solve everyone and everyone should answer.
50 nanometer.
Yeah, others? Is everyone getting
Yeah.
50?
Yes.
Yeah. So D prime is equal to 1.88 D, where D prime is the oxide layer thickness and D is the thickness of the silicon consumed. So upon substituting the oxide layer thickness of 100 is equal to say 1.88 approximately you can take as 2. Then D will be equal to 100 by 2, that is 50 nanometer. So next is the hard copy of the pattern which has to be transferred is called,
Critical.
yeah. So next is yeah, everyone should contribute and finally list the steps that is involved in photolithography. Like one by one, you can try answering. Take a few minutes if you have your notes, so you can just recap and just tell me what are the different steps that are involved in photolithography. Even if you miss a few steps, that's fine. Like whatever comes to your mind when somebody says photolithography, how would the process be like? What is the order of footsteps? Just try to answer. Even if it's wrong, it's fine.
First reticle is made.
Okay, then in yeah, like the others can also contribute and complete. So once the reticle is made, what do you do?
You coat the wafer.
Okay, then so once the reticle is there, then you align it, and that series of steps will be there, right? You apply the resist, you expose the light, those series. Maybe you can just think and just write down somewhere and just read it out loud. Whatever comes to your mind, take a piece of paper, just write down the following steps, and you feel if you're missing some steps in between, just like if you write it down or try to draw a picture, you'll get a better idea of what are the steps. So please take your time, no issues.
Coating, alignment and exposure, developing, etching.
Okay. Coating, alignment and exposure, developing and etching. Yes, one person has answered. Now others, like if anything you want to add in between.
Heat treatment and in the end,
Yeah. Then
Cleaning of the wafer.
yeah, that's the first step. Yeah. So these are basically the steps involved. So first we have to clean the substrate and we have to apply the oxide layer or the masking film. Then we will go on to apply the photoresist. And after applying the photoresist, we will align the mask. And once it is aligned, we will give a UV or visible light or whatever. We are using the source exposure. So once it is exposed, depending on whether our photoresist is positive or negative, that particular region will be developed. That is, it will become soluble and the region of the photoresist will be removed. And finally, we will do a chemical etching process so as to remove our masking oxide film. So that is why the peach color region has also disappeared. And finally, the remaining photoresist will be stripped. The purple color photoresist has also been stripped. And whatever feature we want, that only remains on our substrate. So once this is completed, we will go for the next layer, and once sufficient number or the required number of layers are added, we will go on to the electrical inspection process. So is that clear?
yes, madam.
So these are the nice steps that are involved in photolithography process. So next is the process in which the unreacted resist is removed after exposure is called. So these two questions we are already answered in our non-graded assignment. The person who answered earlier should not answer, somebody else should answer. The process in which the unreacted resist is removed after exposure is called.
Developing,
Yeah. So next is, which of the following statements is false when using a positive photoresist? So before it was like which of the following statements are true. So only one of the options was like directly it was answerable. So now we have to think which of the following statement is false in case of a positive photoresist. So it's rather direct if you see options A and B.
The resist directly transfers the pattern from mask to wafer.
That is correct. So here the question is which of the statements is false. So those are correct. Resist directly transfers the pattern is correct. So this is a correct answer. So you have to tell me which of the following is false. The question is ulta. It's not which of the following statement is true. Like most of these statements are true. One of the statement is false, which is the wrong statement here.
The resist
Option.
layer is applied by spin coating.
No. So if you see options A and B, exposure to light makes the resist more soluble or less soluble for positive photoresist.
Option A.
More soluble.
Yeah. So when the so in case of positive photoresist, exposure to light makes the resist more soluble, right? So option A is wrong. So that is the answer here. All these options, statement B, C, and D are correct. Exposure to light makes it more soluble. Resist directly transfers the pattern. Resist layer is applied by spin coating. All these three are correct. Only one wrong sentence is there here, and the wrong sentence is option A. So which of the following statement is false means that we have to give option A. So is that clear?
Yes.
Yes.
Yeah. So next is SU8 is an example of positive resist, negative resist, solvent or developer.
Solvent.
Others, one person has said solvent, anybody else has any other opinion? So whenever you are going like reading about photoresists or dopants etc., it's always good to memorize a few examples, like few very common or very like commonly used examples. If you memorize, it would be good. Like in case of developers, dopants or sources etc. So SU8 is an example of
Negative resist.
so the answer is negative resist. SU8 is an example of negative resist. So next is which of the following is not a part of the photolithography process? That also we had answered during the non-graded assignment.
Sputtering.
Yeah,
Sputtering.
yeah, that's correct. Sputtering is the right answer. So next is for a 248 nanometer laser source, the minimum feature size obtained in air is dash nanometer. And as a continuation, what will be the case if immersion lithography is used? Everybody take a few minutes, say take your own time. First identify the equation that is used here, then substitute the values and tell me the answer of both 14 and 15 together. Like take your time, solve and let me know the answer.
124 and 86.
Yeah. Others? Did everybody get 124 and 86? So the person who answered, can you tell me which equation you used for 14?
Sigma is equals to k lambda by n.
Yeah. So using the equation sigma is equal to k lambda by na, can others also try now? Sigma is equal to k lambda by na. The sigma is the minimum feature size. K is a constant that has been given to you already in your notes. Then lambda is given to you here as 248 nanometer. And whenever we are doing this calculation for in air, the Na value will be equal to 1. So using sigma is equal to k lambda by Na, is everybody getting 124? Can you please try? K is the Rayleigh's constant, and for people who don't know, it's 0.5. So we're using sigma is equal to k lambda by Na. So now you have k 0.5, lambda is equal to 248 nanometers, and Na is equal to 1. So is everybody getting 124? Others, please answer. So this is the equation.
Yes, 124 nanometers.
Yeah. So for conventional lithography in air, Na is equal to 1. So whenever we are using immersion lithography, the value of Na will be changed. So it will go on to a higher value. And when we are using, usually it will be 1.44. The value of Na will be 1.44. So if you are substituting the all others as same and Na as 1.44, what will be the answer? So whenever you are doing immersion lithography, 86.
86.
Yeah. So in case of immersion lithography, the same process will be done in another medium having a higher refractive index, and that will be 1.44. So when substituting 1.44 in the same equation, sigma is equal to k lambda by Na, we will get 86. So is that clear for all of you?
What
Yes.
exactly is the alpha over here?
Sorry?
The alpha, Na is equals to mu sine alpha.
So, like do you remember the refractive index like equation when we use? So there will be an incident angle, and that will be the alpha. So whenever we are switching the medium, so first it will pass through the interface, and the angle which is made with the interface will be the alpha. So let me see if I can get a picture online.
What advice would you give to someone to have a long life like yours?
Yeah. So here can you see? So this is the specimen, and this will be the oil or liquid or the medium, and the angle which is made by the incoming ray with the normal to the medium and the specimen will be alpha.
Okay.
Yeah. So, like, whatever questions I've prepared for now is over. So I'll ask a few general questions and then I think we can wind up for today. So first, another small point that was discussed in last week lecture was what is the difference between homojunctions and heterojunctions? So can anybody tell me the difference between homojunctions and heterojunctions in case of semiconductor materials? It's a very direct question between what are homojunctions and what are heterojunctions.
Is a junction between same material and junction between different materials?
Yeah. So when the junction is formed between two same materials, it is known as a homojunction. And when it is formed between two different materials, it is known as a heterojunction. So another question is, what are few advantages of ion implantation over thermal diffusion? So these are some kind of descriptive questions that may be asked. So what would be like if you see here itself, you'll be able to understand like advantages of ion implantation over thermal diffusion.
Process can be done at low temperature.
Yeah, that is one advantage. Then from the graph, what can you understand? In case of thermal diffusion, we won't be getting such a profile. So this profile given at this side is for ion implantation. So what can you interpret from this graph? So here is a smaller value, then you reach a maximum value and finally you will get a lower value again. So that is one advantage. So how is this an advantage?
Can we control that?
Yeah. One thing is by changing the energy of the ions that are impacted, we can control the depth of penetration. And also we will be able to understand the range or where the maximum concentration is present. And instead of like the atoms diffusing laterally, we will be getting a concentration gradient. So first there will be a region with less concentration and then there will be a region with a very high concentration and finally again a region with less concentration. So using ion implantation, one is we can control the penetration. Another thing is a concentration profile can be achieved. There is no lateral diffusion and also it is a room temperature operation. And one disadvantage is that it requires post implantation annealing. So that is the case with ion implantation. Is that clear?
Yes.
Yeah. So next one, another question is, which is faster? Will wet oxidation be faster or dry oxidation be faster? So you'll have, I'll just give you the answer now. You'll have to go through the first video and it is based on a few calculations. So the calculations you'll have to go through by yourself. Now you have to just tell me which will be faster. Will wet oxidation be faster or dry oxidation be faster?
Wet oxidation.
Yeah. So do you remember the reason? So basically, based on the set of equations that we had derived, there was a constant B. So you'll have to find out. That is your assignment for next week. We'll have to find out, like go through those set of reactions and tell me what is V. And basically, the value B will be much higher in case of wet oxidation. So that is the reason. The time calculation is done by T is equal to D0 square by B, where D0 is the thickness. So this V value will be much higher in case of wet oxidation. Therefore, for the same thickness, the time taken will be much faster in case of wet oxidation. So one more random question that I had discussed earlier. So I had mentioned about what were the things that is usually present in a photoresist. So what were the components of a photoresist? 4 things were there in Epsom. Most photoresists will be made up of 4 things. And what were those 4 things? Like during the recap section, I had mentioned.
Polymer,
Yeah. What?
solvent,
Yeah. What kind of polymer was it? Was it a normal polymer or a specific type of polymer?
light sensitive
Yeah.
polymer,
Light sensitive polymer. Then we have solvent. Then
additive,
okay. One more thing.
and sensitizer
Yeah. Sensitizer. What was the function of a sensitizer?
to control the chemical reaction.
Yeah. So these are the 4 things that are usually present in a photoresist. A light sensitive polymer, which means that it can change its structure. So there are certain polymers that undergo cis trans transformation, etc. on light exposure. So such kind of a polymer will be there. A solvent will be there. It is usually added to thin the resist, and it will be removed by the soft bake process after application. Then we have what is known as a sensitizer that controls the chemical reaction during exposure. And finally, we have additives in the form of dyes. So these are a few additional questions. I hope like week 2 recap was fine for all of you. Everything is clear. Do you have any additional doubts?
Can you explain negative photoresist ones?
Okay. Yeah. So you see here, what happens is that positive photo. So basic difference is that in positive photoresist, it becomes more soluble when exposed to light, and it becomes less soluble when exposed to light. Right.
Right.
Yeah. So suppose you are keeping a positive photoresist as such on top, and then you are exposing the light. Wherever the resist was kept, that portion will become soluble. That
Okay.
is why it transfers the pattern directly. But in negative photoresist, that portion becomes insoluble, and whatever was there around it becomes soluble. Right.
Right.
So instead of transferring this section, whatever was the negative or the inverse of that pattern gets transferred.
What exactly do you mean negative of the pattern?
Suppose, let me see if I can draw that. Suppose you have a pattern like this. Suppose you
Okay.
have pattern like this and you are depositing something onto this. When you
Okay.
peel off, what you will be getting is this one, right? When you peel that
Right.
material off. So that is known as the inverse.
Okay.
So again, if you want this, if you want to replicate this pattern itself, again you have to use this as your beginning and again transfer, right?
Okay.
Yeah. So that is the inverse. Yeah, and one person had written to me saying that his assignment marks are not yet visible. I think the assignment marks or its review will be visible only once the deadline is passed. I think it's the same for everyone. None of you can see your review right now, right? Whatever you
Yes.
submitted.
Yeah.
Yeah. So only once the deadline, that is, I think it's tomorrow, only once that is passed, you will be able to see the review. And eventually, I think answers will also be uploaded so that you can cross check.
Okay.
Yeah. And has everybody registered for the examination?
Yeah.
Okay. So I think that's all for this week. I hope.
Ma'am,
Yeah, yeah, tell me, sure.
ma'am, for knowing more about that thermal oxidation process, in that there is one model, no,
Which one?
in which there are bulk concentration and other terms.
Okay. The part I asked you to find out, like why wet oxidation, no. Thermal diffusion, let me check.
Thermal oxidation.
Okay, thermal oxidation in that, like how it is governed by Fick's first and second law and how we arrive at those equations. Are you asking that one? Like this part. This part are you asking? Hello?
There is one model no, in which the three flux are given and the equations are given.
Okay, initial part, yeah. Yeah, in that, in steady state
In that,
F1 is equal to F2 is equal to F3, that part.
yes,
Yeah.
in that I wanted to know means that model in diagram. These lines indicate mean a decrease in concentration.
Yes. F1 one towards arrow, F2 in between the gas and the silicon interface, and finally X3, F3 to the external. So you want to know the dotted lines, what they mean.
Yes, and also those flux.
So F1 is basically oxidizing species that has to be transported from bulk to oxide layer. F2 means diffusion through the oxide layer, and F3 is the reaction with Si and SiO2 to form the new SiO2.
And the flux is due to the difference in concentration at the bulk and the source.
Yeah.
Okay.
So in F1 basically they have given an equation, right? Hg is equal to Cg minus Ch. Hg was, I think, the mass transfer coefficient, and Cg and Cs are basically the concentrations. Again, using the diffusion equation, F2 was d is equal to C0 minus Ci by dO. Using diffusion equation. And finally, F3 is basically a reaction rate. So basically, we'll be using Ks into Ci, that is the reaction rate constant. So in steady state, F1 will be equal to F2 will be equal to F3. Yeah, maybe I think just saying verbally won't help. So may I prepare a slide next week regarding the same and then explain?
Yeah, that would
Yes,
help.
sir.
Yeah, I can do that because now just explaining verbally won't make sense, I think. Yeah, so I'll prepare a slide on this one. So I can just give you an explanation of the entire process. Will that be fine?
And
Yes, sir.
Yeah. Okay.
one more thing,
Yeah, tell me.
in the doping, in the video, there was an example that was explained.
Okay.
In that, you took something like ND is equals to 10 power 16
Okay.
centimeter per centimeter cube. What exactly is that?
That is the number of dopant atoms per centimeter cube.
And when you the calculated the depth at which the doping was done, you took the concentration is equals to 10 power 16 per centimeter cube.
Yeah.
Why exactly?
Sorry, I didn't get you.
So the question was to find the depth at which till which the doping took place,
Yeah.
and you took Cx comma p is equals to 10 power 16
Yeah. Because what type of diffusion was it? Was it from a gaseous source or solid source?
solid.
So it was from a solid source, right? From solid source means that C0T is equal to Qt by pi dt. So initially Nd is equal to 10 power 16 atoms.
Shouldn't at the end of the doping, shouldn't it be zero?
Means you are asking whether C0T means at the end of
No,
doping.
no, 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 no. At the end of at the length x, let's take
No,
the
in
length
here
x.
they are asking at C0T means initially, like when the process
Oh
starts,
yeah,
what is the concentration? So whenever the process starts, we have not added any new dopant atoms, right? So here we
no, no,
have an N-type silicon already with Nd is equal to 10 power 16. That is why we
yeah, yeah.
equate, yeah.
Actually understood the zero,
Yeah,
but the question was to find the x value
yeah,
till which the doping took place.
yeah.
So shouldn't we do C of x comma p equal to zero and 0 would be the zero concentration of dopants at the end.
No, at the end, the dopant concentration won't be zero. At the end, we will have a specific value, right? So once we solve for all these things, we will get the value of x.
Right.
Yeah. So first, what we have to do is we'll have to find out Cx comma t is equal to Qt by pi dt. So by 4 pi dt we have to substitute, and then we will have the C value, right? So once we substitute all those things, we will get the X value.
Got it.
Yeah, I think this too I'll have to solve like physically next week. Then only it will. Yeah. So this also I can solve next week.
That'll be helpful.
Yeah, I'll solve it next week.
Thank you.
Yeah. Okay. Anything else? Anybody?
There are a couple of problems in week 2 assignment.
Okay.
Could you just tell what formula is to be employed?
Okay, I'm not supposed to, like, they have given us guidelines not to discuss, but I'll try answering in a indirect way. Can you tell me which are the questions?
Question number 1 and question number 10.
Okay, 1 and 10. Okay. So basically, one is consider the oxidation of single crystal silicon by a dry ox process. If 50 nanometer of silicon is consumed, the approximate thickness of the oxide layer is basically this is the first equation that we had already discussed. Like D is equal, D prime is equal to 1.88 D, right? So in that
Okay.
equation, we had actually cancelled and substituted a lot of things. So if you go on similar lines, you'll be able to answer this question.
Okay.
Yeah.
Okay.
And in so diffusion length, consider diffusion coefficient is given. What is the diffusion length under these conditions? Diffusion length, if you see this particular, let me show you. Here there was, so basically the hint lies in these two steps.
Okay.
Yeah. So if you go through the lecture, root of something among these will is the diffusion length.
Okay.
Yeah.
Okay.
So I hope that's all I can help right now. So once the submission deadline is over, maybe I can surely discuss the answers. But at the moment, I'm restricted to answer the question. Sorry.
Okay, no problem.
Yeah. So I think that's all for today. Whatever I discussed today is clear. And next week, I will discuss the question as well as the flux equations. So that is two things I'll have to discuss for next week. Yeah.
Okay.
Yeah.
Thank you.
Anything else? Anybody? Somebody has unmuted. Vinayak.
No, I'm fine.
Yeah, okay. So that is all for today. Thank you so much for joining. So now you people can feel free to leave. Thank you so much. We'll meet next week.
Thank,
Thank
thank you.
Yeah,
Thank
thank you so much. Hello, Miss Amaravati. Is there anything you want to ask?